So these are applications. So it's important, and we looked at this at the very, very beginning of the year when we were comparing linear, quadratic, and exponential. So we're kind of finishing the year with those exponential examples again. So it'll help you kind of with your final exam because we're refreshing your memory on some of these examples from the beginning of the year. But it's important to know when it would be exponential decreasing. So these are all on the front page decreasing, and on the back page exponential increasing. So let's look just at what are the situations. So you could have your car depreciating in value, radioactive decay of like an element, radioactive element, or a bouncing ball. It slowly bounces less and less and less. Those are all exponential relationships. So here's okay. So it says when representing decay, make sure to use the ratio that represents how much is remaining. For example, 20% decrease is represented by a base of 8.8. So there's 80% of the original amount. So on each of these, you want to think about what correct ratio to use. We're going to set up equations y equals a times b to the x each time. If A is your y-intercept, A is really your original amount. And then B is your rate. How fast is it increasing or decreasing? So a y-intercept on a graph is really your original amount. So you're going to kind of look in the problem for those two values. And then once you have an equation, you can answer some questions. So the first one, Mo owns a construction business and he purchased a new $75,000 dump truck, which depreciates in value 12% each year. If I'm going to set up the equation for this, what's my equation going to be? So 75,000 is the initial amount. What is the rate that I want to multiply by? How'd you get that? Subtracted 12% from 100, right? Right, so you subtracted the 12% from 100. Okay, so it's 88% is 0.88 as a decimal. I don't think we ever divided by anything. Oh, dividing by 100 is, yeah, representing it as a decimal, right? All right, so if I want to answer the first question, how much is the truck worth after 1 year? I'm going to plug in 1. Oh, I guess there's my exponential function. I didn't read ahead, but that's part B. So if we evaluated after 1 year, we would do 75,000 on our calculator. So make sure you know how to type it in yourself, times 0.88 just to the first power, right? It depreciates once. So can someone do that on their calculator and answer part A? How much would the truck be worth after 1 year? $66,000, right? And then it says, how much is the truck worth after 5 years? So you're just going to plug in 5 into that function. So make sure that you know how to type it in with an exponent. Does that make sense? Good, that's what I got too. So anyone have trouble typing it in on their calculator? I just type it in one fell swoop. The exponent key is that upside down V shape to get into the exponent there. Your decimal 0.88 represents 88%. So that kind of makes sense? Okay, radioactive decay. It's kind of the same process each time. The mass, so that's the weight, right, of a certain radioactive substance decreases by 30% each year. The starting mass is 200 grams. So I'll skip to B first. Write the exponential function for after X years. So we're starting with 200 grams. What should I use as my rate if it decreases by 30%? 0.7. I want to know how much I'm keeping. So 0.7 to the x represents I'm keeping 70% of the original mass. So I do 0.7 times 200 to get the weight after 1 year. So after 1 year, it still weighs 140 grams. So the problem with some radioactive substances, it takes thousands of years for them to even cut in half. So if you even have 100 grams of like uranium, it's going to be around for thousands of years. So that radioactivity stays by these nuclear power plants for a long time. And then how much does the substance weigh after 10 years? So we're just going to plug in 10, 200 times 0.7 to the 10th. So in 10 years, it's already down to what, 5.6 grams? So that's not too bad. And then how could I problem solve when will the substance weigh less than 1 gram? How can I figure that out? Two different strategies. What could I do? But what am I going to do with the calculator? Trial and error. So you could keep changing your years up here to 10, 11, 12, 13, 14, 15. Or to me, it's easier to put it into my y equals menu. 200 times 0.7 to the x. Second table setup, I could start at like year 10 and count by a year at a time. And then in my table, it'll show me when I eventually am going to get to less than a gram. So maybe by year 15. Does that kind of make sense? You can use the table, you could plug and chug. So as long as you know a strategy to use like on your final exam or on this test with a calculator, you're good. Graph, table. This is another situation, the bouncing ball. We actually, at the very beginning of the year, if you can remember that far back, we bounced the ball and we figured out the height in the hallway of the ball, and it had a ratio. So this one, the ball dropped from 9 meters, bounces to 7 meters. The rebound ratio remains constant. Find the rebound ratio. Rebound ratio is the bounce height divided by the original height. So for us, the bounce height is 7 and the original height was 9 meters. So the rebound ratio is 7/9, or we could just leave it as 7/9, I guess, 0.78 if you rounded it. So either of those you could use as your ratio. That's the base of your exponential function. So it says find the height of the second bounce. So I'm going to take the height of the first bounce, because that's where I'm dropping it from, and multiply by what? Do I multiply by the rebound ratio, or do I multiply by 100 minus the rebound ratio, do you think? What do you think? What do you say? You want to multiply by the rebound ratio, right? That is telling you the ratio of the height each time. So you have to know when to subtract from 100 and when to just leave it. So 7 times 0.78, about 5.5 or 5.46. And then how many bounces till the height is less than 1 meter? So either plug your equation in, right? It would be 9 times 7, oh no, 9 times 0.78 to the x, and you could plug in different numbers for x or use your table. Why don't you try that one? See what you get for an answer. Because if I just do it, you're never going to figure out how to do it on the calculator yourself. I already know how to do it on the calculator. I would put this into the y equals and then go to your table. But do you know how to get it and justify it? Me too. Good. I'm asking Colin. Did anyone need help getting to their table? So I'm looking at the bounce number for when it is less than 1 meter, so 0.96. So ninth bounce. Did you get that? Okay, so I guarantee if you are following along and trying this with me, it gets you the calculator skills so that when you get to this on your own, then you don't have any idea. Those were all exponential decreasing. So we had car depreciation, radioactive decay, bouncing ball. Those are getting less and less and less. Those are decreasing. On the next page, we've got 2 examples of increasing, and then I have a couple examples you're going to try on your own. So this one says when representing growth, use the ratio that is bigger than 1 by the amount. For example, 4% growth would be represented by a base of 1.04 because you have 104% of the original amount. Does that make sense? So for decreasing, use what you have left. For increasing, you're actually going above 100%. You have more than what you started with. So if Emily needs to save money for college and she plans to invest $1,000 in a bank account that earns 2% interest each year, it's compounded every year. Compounded annually means every year. So it's growing by 2% every year. What's the value in the bank? Write an exponential function and then find it after 10 years. Let's write our function first. She's investing $1,000 and she earns 2%. What should I use as my ratio? What? You're right. 1.02 raised to the x power. So now you can plug in 1 year, plug in 10 years on your calculator, see what you get. It should be growing. So if you were doing this correctly, year 1 should be just $1,020, right? That should make sense. 2%, you could do that one in your head probably with 1,000. So then try to do the 10 years. It compounds again and again and again. That's what you want at annual compounding. So did someone get an answer for 10? What'd you get? 1,219. Yep. So not gaining a whole heck of a lot over 10 years. 2% is pretty low interest. All right, so that's increasing money. And then this last one is population growth. Jamie's working in a biology lab with bacteria. There are 4 colonies present. The colonies are tripling each day. So find the number of colonies present after 1 day, find the equation, and how many days until there's 200 colonies. So let's write the equation first. She's starting with 4, and it's tripling. What should I use as my ratio to show that it's tripling? Yeah, multiplying by 3 each day, so to the x power. So you can do the first day and then use your table to figure out when you get to 200. So see how it's the same exponential type function each time. So by doing it over and over, that should be able to stick, hopefully. So don't say it out loud. See if you can get it. And then I'd like you to skip the credit card debt problem, number 1 on the next page, and just try situations 2, 3, 4 on the back because they're very similar to the ones we just did. So for the end of class, you have still 10 minutes till we'd be finished. You should be able to finish 2, 3, and 4 on that back page, but please cross out the credit card problem. It's just too long for today. I'm not going to go into the credit card problem. Let's see, did you get 1 day? It would be 12 colonies. I said by day 4. Does that sound right? Okay, so if you can do those problems, you should be able to do these situations 2, 3, and 4. So I'd like you to try them and then we can check our answers.